Hello, everyone, and welcome to another episode of Solving Advent of Code in Rust. Although we're not going to be streaming too much Advent of Code today. The goal is to learn Rust as much as we can. I'm Eugene, and we have,
Hello.
and not very visible, but
Roberto here. Hello.
thanks everyone for following along. I'm not going to tell you too much about Advent of Code. In short, it's just a series of challenges that are published every year in December. We try to go through these and learn Rust by solving the challenges in there. Last episode, we merged exercise 6 from last year, but this episode, we're going to be running it on a Raspberry Pico, and Roberto is going to be showing you how to do that. I should mention, sorry, because this is a different intro than usual. I should mention that we have the code on GitHub. Apologies, and we should get a banner for that. And we publish recordings
Yes.
on YouTube. So every day after we stream, this should be visible on YouTube. If you're watching this on YouTube, we're streaming this on Twitch every Monday. So link should be in the description.
This code probably will go in a different repository, I don't know, or as application in the current one in a specific branch. I still have no idea.
Yeah,
At the
we'll
moment,
make it available somewhere.
Yeah, we will make it available somewhere, but at the moment it is committed nowhere. So I hope my RP400 is not burning. What is the hardware setup for today? For today, we are running inside a Raspberry 400, that is basically a Raspberry P4 with 4 cores, 4 gigabyte of RAM, and is the usual Linux machine that is running. It has GPIO that are handy because we can connect them on a breadboard. From the breadboard, we have 3 pins that are those 3 pins that goes in a connector that is here in a Raspberry Pi Pico. Those 3 pins are used for debugging and programming. It's also possible to program through the USB serial port, the USB port that can be also used as a serial port, and is also providing a USB drive, and you can drag files in there and program them. The problem is that you can't debug on top of this port, and the problem is also that it's a little bit tricky if you are iterating fast to change the program very often, because you have to reset it, keeping this button pressed. Then you will have a drive, you drag the file, you release it, it reboots, and start executing your program. Instead, on those 3 pins, you can basically on the fly program, debug, and do everything. Okay, those 3 pins are connected. Then there are power, ground, a reset wire that is here pending. This is the power switch, as you can see.
Looks totally legit, yeah.
Yeah, 2 serial ports, because later, if we have time, we will show also some serial communication back to the Raspberry. And this is an oscilloscope on a specific pin on the board, if we are able to make it work with the probes. So, what are we going to do today? Today, we are going to show you a very minimal Rust code that is working on any embedded platform. We are doing this for the Raspberry Pi Pico. So let's start. At the moment, as you see, I'm on the Raspberry Pi 400, the Raspberry Pi 400. First of all, this is our main. First stuff to say are those 2 features: no main and no std library. Why no main? Because the boot of this stuff is not like a normal Linux process inside a Linux kernel. There is no real entry point. The entry point is an hardware point. When you reset the device or when you power on the device, the program counter jumps to an address and start executing code from there. Nothing else. So it's not exactly a main function. And why no STD? and here, Luciano, if you want to say something too. But basically, no STD is because this hardware has memory. It has a 256K of memory. But it has no IP. It's just stuck because the IP is managed by the operating system. But this guy doesn't have any operating system. There is nothing if you don't put a program in there. So exercise 6 has the plus that it runs only with arrays. So running only with arrays is perfectly fine. You can allocate your array, you can work with your memory, but you don't have the ability to allocate. So we are not using vector, we are not using maps. There are libraries, right, Luciano, to allocate memory even only in stack, right?
Yeah, we haven't tried those yet, but
No.
there should be different ways. I think one is to use libraries that use the stack and give you functionality similar to the one you will get with the standard vec, hash map, etc. And other ones, they will probably pick an amount of memory, assuming that you have ways to allocate arbitrary RAM memory, and you'll need to bring your own allocator and use this allocator, and then you can probably use the standard vector hash map, which are also available in Core, I think. So my understanding is that Rust gives you this abstraction where by default you get the standard library, and the standard library assumes that you have a full Linux-like operative system with allocator and with system calls and all this kind of stuff. Instead, when you say no STD, you're basically using a subset of the standard library that doesn't make all these assumptions. So you have kind of a lower level abstraction that you can use. And we'll put in the chat a very good guide which gives you a little bit more detail on all of that, how it works and how it's structured. Yes, feel free to continue, Robert. I don't have anything else.
Said so, this is the bare minimum application you can run on top of a hardware. Is doing nothing in a loop. And before that is putting 42 in a variable that we are not using. What to point out in this? To point out that we have no main, we have a function called reset. That is the function that will be called at the reset of the device. This is an unsafe external C function. Let's watch this. This is called a divergent function, I think.
Mm-hmm.
Basically, this is telling that this function is not retarding. Normally, when you write on top of Linux a process, you return void or you return an integer from main that is the exit code of your application because you have an operating system outside that is getting that number and doing something with it. Obviously, here like we said before, we don't have an operating system, so we are doing nothing. If we exit, where do we exit to? There is no out there. There is nothing out there. And so we stay in our loop doing something or nothing in our case. This is basically a variable of that type of function that is pointing to reset. And there's a link to a vector table reset that I will show in a moment. Then it also has a panic handler if there is any kind of panic from the usual overflow integers or the usual negative numbers in unsigned integers that Rust is doing. Again, what do we do if we panic? We do nothing because we could write something on the serial port. We could log something if we have a memory somewhere else, but then we have to halt or wait for a reset or reset ourselves. But in any case, in this example, we are just doing nothing. What are the important parts for having this bare bone code? For sure, a main RS like this, a cargo to ML that is containing our application. Our only dependency is Cortex-M to be able to call NOP. There are other ways of putting assembly in line, but you have to use nightly builds of Rust and is a little bit a mess. And what to do in case of panic? That basically give up. What do I do if I panic? I give up.
Fair enough.
Another important file is this one, link.x. Link.x is basically the linker file. When you compile the application, you convert the code into assembly. Then the link file, the linker, know where to put this assembly, because where do you put the assembly? Basically, this file is describing the hardware of Raspberry Pi. Those numbers can be different for other silicon, for other hardwares. Basically, it says that starting at this location, we have 2 megabytes of flash. Starting at this address, we have 256K of RAM. It says that we enter in the reset function that has an external reset vector, that has a vector table that will be put in the flash. Then it says that we have text that will also be put in the flash. Text is if you are code some strs into the code, they will go here. Then it's initialize the pointer, the stack pointer. The stack pointer go at the end of the RAM. So the pointer of the stack pointer is the start of your memory plus all the length of your memory. So the stack pointer is there because the stack is decrementing every time you push something to the stack. This is the reset vector itself. Then I have no idea what this discard is, but probably it's discarding some registers because we are not using them probably, but I'm not sure what this discard part is.
Did you get this file from an example, or
I had to dig for this file and change them a little bit. Basically, I looked in another boilerplate that we can show later, but this other boilerplate had also another section of 256 bytes that were used by a specific library to create a wrapper around your application. So this minimal application has no wrapper around it. There is, like we said, there is nothing out there.
okay.
And for this reason, we have this very unsafe and ugly code here because there is nothing handling. We are not presenting a function. We can show it later, the more fancy way of doing this.
Yeah, the only thing I know there is that extern C and no mangle are basically done so that when it's compiled, it retains that name reset. So it's actually able, the linker, to connect correctly the address of memory of this function to wherever it needs to be.
Yeah, because here we are calling it by name, so it must not be changed, because if you change it, it's not able to link it anymore.
I think by default the Rust compiler otherwise doesn't give you any guarantee that the name will be reset.
Exactly. Here there is also in the .cargo file a config toml file that has some important stuff to show. One is which file to use to link, is written here. Pass to Rust C, cargo must pass to the Rust C binary, the parameter -c link argument -t link.x. So here is where that link.x is used. Here there are optimization that I commented, all of them, no vectorializing of loops, frame pointers inline, all stuff that I wanted to see the bare minimum stuff needed to create my executable. Here there is a target folder. Our target is this because we have a Cortex M0. If you have a hardware with other type of Cortex CPU, you have to uncomment the right one and do a cargo install of this specific platform. I only did cargo install for this platform because it's the one that we are targeting. This syntax is use these parameters for all the ARM when you compile against all the ARM. This is exactly probably not the right way of doing so. I could have said do this configuration only if you target this specific type of platform, but we are not cross-compiling it to multiple silicons. We are compiling this only for this one. Yes, it's a little bit simplifying the problem, but please.
You could make it more generic. Basically.
Yeah, you can make it more generic. You can make it more specific. You can add multiple support for multiple platform. We are not going to do that. Say it so. How do we compile this, and how we flash it to our hardware, and how we check if it works? Do you want an answer to this?
Yes,
Yeah,
please.
how we put it there? Yes, please. How we put Rust inside this one? But well, Rust is a cargo build. Let's not do a release. Let's cargo build. Okay, unoptimized debug info. What did we build like this? We built a file called in our target folder, in our th debug rp40 minima. It's a 77K file that contains our code. If we see what do we compiled, we can use a command called cargo object dump, not release, because we want to say we want to see the debug version of it. Okay. This is elf32 little arm. Disassembly of the section. What do we have? We have saved those two registry to the stack. Add the stack pointer to R7. Subtract to the stack pointer 8. Put 42 in R0. Move store, str stay for store, R0 into the stack pointer +4. Why +4? Oh no. Then branch jumping to immediate -2. Then again, it jumped to our cortex nop. That was our function. Cortex nop is this function. It jump here. When you enter in a function, you save the registry, you add, you see this is boilerplate. Then you call nop, that is another function that is down here, that is doing nothing. bxlr is like a return, so it's returning where it was called. Then is branching again, popping the variables with also the program counter from here, because it saves where it was, where it has to continue the execution. But basically it will jump back here, and then it will start to loop infinitely in those three instructions forever. How do we write this to our Raspberry? We start a tool called OpenOCD. OpenOCD is a tool that is used to program through JTAG all a bunch of different peripherals. So it's not just for Raspberry, it's for everything that has this protocol enabled. We have to tell what kind of programming interface are we going to use. We are going to use a Raspberry Pi SVD, that is this connector that is on the breadboard down here. So we tell him that we are going to use this type of connector with this type of connection, with this type of wiring. That, sorry, I have to raise the paper to show you this slide. So basically, pin 24 go there, pin ground go in the middle, and pin 25 go on the right. So from this connector here to this chip here, okay, with 3 wires like that. Then we have to power it on, because if I don't power it on, it's not going to work. Oh, it's powered on. Now, if we go on the terminal, Luciano, can you? Thank you. Grazie alla regia.
I feel very useful today.
The chef target. Our target is RP2040. That is the name of the chip on top of the Raspberry Pi PICO. The 2 stands for the number of cores. We have 2 cores. 4, I think, is the number of bank. There is if you take a look in the data sheet for the chip, those kind of numbers are explained. When you run this...
sorry, Roberto, just a quick question. So that file, Raspberry Pi SWD CFG, is it like a text file or is it like a binary file?
This is a very good question. I have absolutely no idea. We can take a look.
It's not something you had to create yourself.
No, it's something that comes with OpenOCD.
Okay.
That is probably somewhere here. Let me take a look. There is an OpenOCD.
So I thought that you had to manually tell the pin configuration somehow. Instead, it's like a standard. You just need to follow that configuration, right?
Yeah, there is a standard. You can change them if I'm right, but why? So why do you have to change them? Use them like they are, and
No, I actually prefer that there is a standard, but I was wondering if you had to define the configuration yourself, or it was just, yeah, this is what you need to do.
It is somewhere here, but we can take a look. For example, let's try to find it. Find into my home dash name Raspberry PSP. What I
Not Raspberry.
Raspberry, yeah, it's the new one. The new one. Okay, sorry, but those machines are not the fastest one. While we answer this question, okay, is there? Let me stop this and let's cut this guy. Copy, cut. It's a text file, yes. Adapter, driver, BCM, GPIO, speed, pins 25 and 24 that are the one that are written in the paper here, 24 and 25. So 24 and 25. So they are the two pins that are written in the file. Transport SVD, adapter speed 1 megahertz. If now we start it, then there is also the target that is probably explaining something very similar. Let's see if we can cut also the target. That must be in the same folder except target rp24.cfg. Yeah, it's telling core 0, core 1. Here we have way more data.
But basically, this tool needs to know from your Raspberry for the one you are using right now, the one you are streaming, how to connect to the Raspberry Pico
and then
to send all the data.
Yeah, it must know also some data around the Raspberry Pico because it must know where to write stuff.
Because it could be any generic hardware supported,
yeah,
right?
because
So
can be any generic hardware supported, and these addresses can be different because is basically how you create the chip that is tell you where the memory is. Big endian, little endian, all this kind of stuff. Flash base, flash size, and so on.
Okay.
So now that we have removed this curiosity, we run it. Basically, what it's doing is connecting to those free wires that I showed before at 1 megahertz, that is the speed that was in the file, is connecting on top of those free files that land here. So those three that we have here is connecting to the Raspberry, opening local ports, is opening a local port that is free. And now we can, with GDB, send commands to that port. So back to the terminal. Here we have with cargo build compiled our binary. We know what it is. Now with GDB multi-arc, we can take our binary file. Okay, now nothing is happening yet. We are just started GDB with that binary. What we have to do is doing target remote free. That is the port that is provided us by this one, and you say new GDB connection, target is RP2040 core 0, state altered, preferred command is extended remote instead of remote. Okay, I already missed that command, but okay, extended remote next time. Now we have to load. Load is sending to the flash in the silicon, in the hardware, our program. 21 bytes written because our assembly code was 21 bytes. The file on the disk is bigger because it also contains all the linking informations and all the other stuff. So it's not exactly the file that we have to write. It's a representation of our code in assembly plus information of where to write them. Okay. Now, if the program is still not running, we can start it. Const. Now, this program is doing nothing in a loop, so you are not seeing anything happening, obviously. Now, what we can do is breaking it, jumping out of the current function and list. Look, this is our code, the code that we have in our editor. We have our current point that is blocked on the Cortex ASB NOP. This is not optimized version, so I think I can get the value of x. X is 42. We assigned it. We say print x, and we have that x is 42.
This is because GDB basically acts like a bridge between the code you have in your main laptop and the code you have in assembly running in the Raspberry Pico, right?
In assembly in the Raspberry Pico, there are all the pointers, all the breakpoints, and the symbol table there. GDB is also having access to the source code because it's there.
Exactly. Yeah.
And so can show me the source code. The source code is not obviously in the hardware. The source code is on my machine. Is not exactly my machine because it is in the Raspberry Pi 400. Now I'm in another machine with a normal keyboard. Thanks God. And yes, you can step. If you step, you go inside code, and this code is inline callout. This is the code of the library that we are using, of the Cortex-M. Then you can step again into it. Okay, it doesn't have the code for this. We are here. It know that we are at this program counter, but it doesn't have this file, so it's not able to show us the code. Makes sense. Finish is going to jump the level above, so we are still in our function because we are looping here until we die. If we do cont, the program is just continuing, going on, but we can break it with Ctrl-C again. We will be always on the same instruction because there is only one instruction. So this is our program. What can we do now? And now let's enter in the advent of code. If you don't have question, we enter in the advent of code part. Do you have question? Is there any question in the chat?
Nope.
No.
People is already suiciding and taking a nap.
Or they went off buying a Raspberry Pico.
Yeah, or they are taking a nap and my voice is cuddling them. So now we have to import our library dependency. We wrote our code as a dependency. So let me see if I can find. No. I have to cheat a little bit and look how I import our library.
Meanwhile, I can explain what's the idea. So basically, we have all our code for the solution of Advent of Code in a repository on GitHub. And Cargo allows you to include dependencies, not necessarily from crates.io, which is the main registry, but also directly from GitHub. So this is what Roberto is trying to do. Even cooler. Yeah, no, go ahead. You can explain that.
No, go on. The syntax is this one. Go on.
Even cooler than that is that our repository is structured as a monorepo, which means that you basically have multiple projects in one repository. And to do that, we are using a functionality that Cargo gives us that is called workspaces, I believe. And basically, when you do workspaces, it's like you have a collection of libraries in one repository. And here, the first part of this syntax, we are basically saying import specifically that one library. So this way, even if we have a project, a source code with multiple projects, we are very able to target specifically one library and import it directly from GitHub, which I think is pretty cool. It doesn't happen in many other languages as far as I've seen.
Quick question. Assuming we would have a cargo toml and stuff, could you point it to a folder directly? Like, could you go to github.com/user/project and then go into the folders of the thing?
No idea.
I'm not sure. I think this is the way that you will do it with the workspaces. By the way, here we're also using a branch because Roberto had to do some changes
That we
So
can
you
show
can-
that we can show later.
Yeah, you can also target branches. I'm not sure if you can target subfolders arbitrarily, maybe, but I think you still need to have a cargo toml somewhere.
Yeah, I was asking because I know we did the workspaces thing and we add every exercise there, but I was curious if it's looking at the root and then trying to find the project, or if it just cares about a cargo project definition. Like,
I think it needs to find. I think it needs to find a cargo toml. So maybe there are ways that you can just say, look for a cargo toml in this folder.
Fair.
We
Anyway,
can
let's
look
go
for
back
that.
get back to Roberto showing us how to run this. Sorry for derailing it.
But well, let's just show, obviously, take it. Sorry, guys, but the Raspberry Pi 400 obviously is not the fastest machine on earth. So we are going slowly to our cargo toml. Okay. The members are all of this. So here you specify the subfolder, and then in the specific folder you have the name of the project, of the library, because those are all libraries in the end.
Just figured it's a good time to say this is a public repository, so you're very welcome to contribute.
Yeah.
Banner coming, if I can find it.
Yay, banner. So here is the name of the library that we are going to import. This name must match what we wrote here. Otherwise, it's not going to match anything. Now that we imported it, we have to go back to our code. It was in this tab. We have to use it. Use 1x06. I was complaining probably that nobody is using it. And use the import. Rust, you're always the same. Now we wanted to give it an input. There was the input from the README attend.
I think if you use part 1, the input will be already. Oh, no, we need to include it, yeah.
We need to include it just to do something a little bit faster. The scrolling is... okay, let's take this, that it was our...
Yeah, we are lucky that in this exercise that the input is relatively small. It's like one line.
So we can... I don't know if we can assert here.
I don't know if assert is in the standard library or not. Let's see.
You are. And what was the result from the README again? I don't remember. So this guy, after 80 days, 80 days was the 5934.
And you want to do assert underscore EQ, I think.
Underscore, sorry.
Yeah.
Okay, so you can assert. That's pretty good.
Well, let's see if it runs.
Let's see if it compiles.
Yeah, fair.
This is the step before. Cargo build. Okay, he's downloading. Perfect.
That seems unhappy.
Okay. What is complaining about? Linking with Rust LLD. Okay, it's trying to link. He downloaded the library, it's trying to link. No memory region specified for session, read-only data. Okay, now we have to specify a section for read-only data. Cool.
We probably need to directly import assert.
So just a second.
So I think you can try to use core column assert underscore EQ.
No, rodate. Rodata. No, rodata.
Yeah.
Okay. We have to Google this in real life.
Sorry, Roberto, can you try something very, very quickly?
Yeah, sure.
So there are, I think, two possible solutions. One is
Yeah.
to remove assert EQ and just use assert, and then you manually do equal equal.
Mm-hmm. And assert is a statement or a function?
As a no, with exclamation mark, it's still a macro. And now you can do that equal equal that. That might work. Otherwise, they say assert EQ. You should probably use core column assert EQ. Ooh.
Oh, you're not in the right folder
I'm in
anymore.
the wrong folder. Sorry, I moved. I think he doesn't know where to put our string.
Okay. So maybe we'll need to change that boilerplate that you showed.
Yeah, the minimal boilerplate was too minimal. So, and also we have to say Rust because this is C. Okay, I already saw an error like this.
Okay, I think I saw it.
Mm-hmm.
Let me share this one with you now in the chat. So there is a section called Life Before Main, where they show you how to update that template, that link.x, to expose raw data.
Okay, I can't open it on the Raspberry because I'm not able to copy there.
I think if you search, what did I search?
Oh, no,
Rust no std raw data, you probably find it. Yeah, that's the one. And there is a section called Life Before Main. If you keep scrolling, I think.
Okay, this is the disassembly.
Keep going. Yeah, almost there. There you go. That's the one.
No, raw data. Yeah. And data and VSS, all these ones is due.
Do you think we need the text as well?
Which text? The text I
The
think
one
is
on
already. Text I think is already there.
Don't remember.
Text.
Oh yeah, it is. Okay, cool.
So he was not knowing where to put the hard-coded string that we were writing. So it must be put in the flash.
Cool. Let's see if it compiles now.
Makes sense. And now is it compiling? Okay, at this point I can try again with assert EQ.
Yes. I'm curious if we need to use core column or not. Okay.
Core probably is imported by default.
I don't know. I just found somebody saying that for assert EQ you need core, for assert you don't. But maybe it was a bug and it was fixed.
Now is way more assembly.
Yeah, that's a lot. But then we're doing a lot as well.
And my terminal ends here, so there is a lot of instructions. Specialized div rem U64 div reminder. Are we using div reminders?
Probably to calculate. Did we change that? I'm not sure.
We had a modulo, right?
I don't remember which version are we using, but in any case, let's see if it works. Now, we built, right, let's start at this point the debugger again with the same file, because the file is always called the same. We target, you can automate all of this. I'm showing it because I'm showing this because it's no such file. Oh, well, fmt mod rs, there is not the file to show the code. Who cares? Code. Okay, now we have 5,717 bytes that are way more. than before. And if we list, can we list? No. Let's count. Let's break. Let's list where we are. We finish. Now we are where? We are in a range RS, so here we are in iter range. Let's go another level above in the stack. Here we have an option. Here we have an option. Here we have sum. Here we are in a result. Here we are in a sum. Here we are in a set equal. So if we list, value returned done from $4 is 5934. That is our value. Now, let's make break on line 17. Now we put a breakpoint there. We can continue. Oh, it's blocked. It's blocked on the. If we were smart, we had put that in a variable to be able to print it.
All right. Yeah.
Okay, let's change the code.
You cannot invoke arbitrary functions, right?
No, I don't think you can. You can only dump registry and variables. Yeah, it's not that. I don't think. I think on bigger machines it's possible. Here it's just probably dying. And our result is this guy, and then we put.
You need a semicolon, yeah.
Now let's build again. Let's not the dump because it's going to get extended remote. I will show you how to run this with a cargo run because it's faster. Okay, it kept the breakpoint from before, I think.
That's cool.
This is because you have a server that is running all the time, right? A GDB server.
Yeah. Let me clear the breakpoints. No breakpoint at this line. Clear 18. Clear 17. Clear 16. Let me quit. This happens because I'm not completely aware of how to reset properly this guy. I will reset it just powering it off, removing this wire, powering it on again, just to throw a reset with this wire on this pin. Done, resetted, beautiful. And then target, we go back to the terminal, extend the remote on port 53. We load the code, we run the code, and it's running. We break the code, it does random point, we finish, we finish. Every time I write finish, we go one level above in the chain of codes. Now we are here. Now I put the break point on line 17. That is called break, not breakpoint. I count. Okay, print res, and is 5934.
Perfect.
So we are able to call our function. We are able to put it in a variable. We are able to assert on top of it. Obviously, at the moment, we don't have communication with the outside of the chip. Everything is running, and our only channel of communication is the GDB connector on top of those 3 wires. But still, this is running on real hardware and doing its stuff and producing a lot of code. Now I can quit and quit. What do we change in that branch? Can you share your, Eugene or Luciano, your screen?
I can share it, I think. Give me a second. It's in a branch
called
the RP PICO.
Yes. So let me go there and share this.
I'm asking to share to you because doing that on the Raspberry Pi 400 is painful, at least.
I make this bigger. So we go 2021, exercise 6, and then source and lib. So that's the file.
What changed here? For point one, you can't import a library that is not no std in a main that is no std. Because obviously, if your library needs the standard library, but your main doesn't have it, game over. So we added that. The trait from str is again from the standard library, so I commented the line. The line
which also means that we'll need to do something different, because initially we were using from str to parse the input.
Yeah. The rest of the code was usize everywhere, if you remember. Now is U64. Why this? And this was tricky to debug. Usize change based on the platform. On our laptops, probably is a U64 or a U whatever. On the Raspberry PICO is a U32. So part 2 was failing because the number was overflowing with a usize. So I had to explicitly say, no, is U64.
Did you get an overflow error or just didn't match the assertion?
No, it was going in panic.
Okay.
Directly.
That's actually better than
Fair enough, yeah.
the randomly giving you a number that is not the right
No,
one.
it was not doing like C, that is just going back, overflowing and going back to the minimum. It was going in panic mode. Everything was halting, and I had to reset through hardware the chip. So probably game over. Nothing left to do. So all the U sizes now are U64. If you scroll a little bit again, there are no changes to the code at all.
Yes, by the way, we have a question meanwhile. Let's answer the question very quickly. So Mizard is asking, how would you get the PICO to report the results without GDB?
We have another source to show. This is a good question, but we can answer later, okay?
What we did before, I don't know if you saw, that was literally just checking the assertion, so that will either panic or not. And also with the debugger, we were checking the variable value. But there is a more sophisticated way. We'll see in a second.
Yeah.
Okay.
All our stuff, the code is the same as the other branch. The code didn't change except for the type, our
U64, and then we implemented this from string directly rather than using the trait.
That was there. It's just a function that is doing exactly the same. The code is exactly the same, just we are calling it on top of input instead of doing input parse.
Exactly. Here we were doing input.parse.unwrap. Now we are just calling this function.
Yeah, it's the only difference that is there. All the rest, and I removed some tests because they were testing stuff that were. I didn't want to fix the test. I removed them.
Yeah, fair enough.
I left just the two important ones.
Yeah, this one is the value that was overflowing.
Yeah, it was overflowing with a U32, with a U32, with a U size on the Raspberry PICO. That value is too big.
And I suppose that's the lesson learned for us. Don't trust U size as a U64. If you need a U64, just use it as a U64.
It's fine if you are on a brand new, on a 64-bit machine or on a new machine, but this is new, but not very big machine.
Fair.
Okay.
So not a lot of changes, to be honest.
I suppose here we were lucky because we were not using any allocation. All the exercise was pretty much doable with arrays. And that's it. We didn't even need strings or stuff like that.
Yeah, but even the exercise that we did with vectors, in the end, it was doable with when we do vector with capacity. When you do vector with capacity, what is preventing you from allocating an array?
Fair enough. Yeah, you just need to keep track
of the length,
of how many items you have already written. Yeah.
You need another variable length for that one. You can put that in a struct and creating your own vector. That is
mini-vec, yeah,
it's a vector with just a fixed amount of capacity and wasting memory. But if it's fine for him, fine for me.
Okay, so do you want to show?
Yeah, I want to show another version of this that has way more boilerplate. But this is the bare minimum to have something running. You saw there is the linker file, a little bit of code. You can import libraries, say you have a main function. So from here you can go on. Now I will show you something else. Is another version of this took from a boilerplate that is a project called RP 2040 project template. Git.
I'll try to find the link and put it in the chat.
Origin. It comes from here. This is the boilerplate that I took and modified.
Perfect. I'll put it in the chat.
Let's start to see what this boilerplate has more than our code. First of all, it has way more dependencies. Cortex-M RT, embedded HAL, that's say for hardware abstraction layer, embedded time because I wanted to take times to see how fast it was to run. The FMT RRT, panic probe. Panic probe is that piece that I was saying that is using 256 bytes of memory. RP PICO, that is a crate for the RP PICO. Again, our library that you see. This is the only addition that I did to the cargo, adding our library. Then again, let's jump to, I put in our input file from our exercise. This is the real input that we are doing in exercise 06. Where is it? Where is the main? Where is the main? Main, where are you? Here.
Insert, yeah.
Yeah, sorry. A moment. Going here. Same start, no standard, no std, no main, import of a bunch of stuff, import of RP PICO, SBSP, abstraction layer, core FMT write that is used to write to the serial port, and our library. The main is a function at this point that is annotated with entry. There are libraries here imported that do all the extraction that we had to do manually on the other file of having the external C with the vector reset point and all of that. In the end, all of that, there is a wrapper around it that is creating, that is basically you can decorate this main that is always a divergent function, always not returning with that. Here we were trying to allocate a lot of memory just to play around. So we allocate 128K of U8. This is all boilerplate to initialize. This is initializing the pins to do I/O. This is initializing 2 pins, one for the LED and one to pin 15 that is connected to our oscilloscope here that we'll show in a moment. Then we are initializing the pin for the serial port, WART. We are initializing it as 9600 baud, 8 bit of data, no parity, and 1 bit of stop. Yeah, no parity, 1 bit of stop is in the comment. Cool.
Not sure if carry on. Yeah.
Yeah, is here. When I over is 956, 9600, 8 bit data, no parity, 1 bit of stop.
This is what will give you the terminal, basically, right?
Yeah, this is giving me back something. I set up a counter, this counter from this number back to 0, then back to this number, and again. This is counting in nanoseconds, microseconds, sorry. This is counting in microseconds, so every microsecond there is a tick. This is hardware, so it's independent from our code, and I'm using this to do the performance of the code. Then I write something, I write the frequency of the CPU, that by the way is 120 megahertz. Then I'm bringing up the lines of the LED and of the GPIO 15. I'm taking times, calling part 1 with the bool input, computing the delta, doing the same for part 2. When all of this is done, I bring down the line, I turn off the LED, and I bring down the line 15. I just do something on the data to to make the compiler happy. And I write on the serial line, part 1, this result, this time in microseconds. Part 2, this result, microseconds. And again, I increment the loop counter by 1, and I jump back to my loop, and I execute forever.
Can you zoom a second on that write, just because I think that answers the question that we got, which is basically once you have a serial, you can write into the serial, and you can create a serial terminal, connect to it, and basically you'll see the output in that terminal.
Yeah.
Is
that
correct?
Yeah, it's only using one wire because the communication is only from the Pico to the Raspberry to something else, and it's only one wire. I connected also the other one because I was thinking of doing way fancier stuff than I didn't at that time. So a little bit more boilerplate because there is all this initialization of port timers and stuff like that, but obviously is able to do way more stuff. And there is an abstraction layer that gives you the ability to bring a line up and down just doing GPIO, GP15, set low, unwrap. Also, the communication is unwrap because otherwise I think it's not blocking, it's asynchronous, but well, who cares? Let's not go down that rabbit hole. Now,
I think because in general writing can fail, so you need to handle the error.
If we are lucky, everything is right, is working. Demo effect. Let's see. Cargo build. Okay. Here, let me try this. It's not always working. Okay, now if we go to the hardware,
let me show.
I wrote cargo run. Cargo run executed what I was doing by hand before. OpenGDB, remote stuff, and start. Cargo run executed what I was doing by hand before. And I will show you in a moment how to do that. Now we see that the LED is blinking. And here we have data on our pin. Let me just change the trigger mode a moment. Okay, now it's stable. So this is the execution time of our code. The code is starting, the line goes up, the code is executed. When part 1 and part 2 are done, the lines go down. Every square here is 2 milliseconds. So we see that are 1, 2, 3, 4, 5, 6. 6 or 5? 6, the same 6. So it's around 12, 6 is 12 milliseconds of execution time. And this is running. It's also sending data on the serial port. I probably can show it, the data on the serial point, moving the probe. Let me just take this wire, moving it here, and plugging it here. Okay, those are the data on the serial port. If you see, they are at a different speed. They are going fast. They are up and down based on the value that they are sending. So serial port is working. Let me go back to our GP15. This is GP15. And the LED is blinking. It's blinking regularly. You see that blinking in a strange way on the webcam because the shutter of the webcam is not in sync. If we go to our terminal and we open a new terminal and we open a serial something, that in my case is Minicom.
Mm-hmm.
Can you channel switch to the terminal?
Yes.
I'm saying Minicom open port dev serial 0 at the speed that is also in the code. And we have our Raspberry PICO sending us back data on what is happening. So let me stop this so we can read. Control A. We are at loop 1643. Part 1 result is 350149. That is right. I hope. I don't remember, but I think it's the right one. And it took 5 milliseconds, 5,000 microseconds. Part 2 took a little bit more because instead of 80 loops, it's 255, 6 loops, and took 6 milliseconds. Remember, we are compiled in debug mode. So try to remember those numbers.
Huh.
But well, to be honest, I can leave the terminal running in this terminal. We go to where I run cargo run, that is here. I'm going to quit cargo build. No, I can do just cargo run dash release, I think. Then const to start the program. If we go back to the hardware, sorry Luciano if I dammado. So here we can see that this spike is the spike of the execution time. Now that we are in release mode, is way smaller. Is more or less half a square, so it's more or less 2 milliseconds. Let me change the
before
time.
it was like 6 blocks, right?
Yeah, before it was 6 blocks. Let me just change.
So it's like time. 12 times faster, roughly.
Okay. Now every block is 0.2 milliseconds. So everything is 5 blocks, so it's around 1 millisecond. Okay. If we go to the serial port now, what do we have on the serial port? On the serial port, let me block it. We have, again, looping, the same result as before, but now the times, instead of being in thousands of microseconds, are in hundreds of microseconds. So summing them together plus some overhead for the communication and everything else is more or less 1 millisecond of execution time. Then we communicate through the serial port blocking, then we loop again. So between the spikes, we have the time of the serial communication happening. We could write another thread because this hardware has 2 cores. So we are running only on 1 core. We could run on 2 cores, and one can handle the communication and the other one can handle the computation, but it was complicated.
Fair.
So here the stuff are running, and let me just go back to the code. What is the code? Yeah. So here we are communicating back. We are using the library that is the same that we were using in the smaller example. And we have a little bit more boilerplate. The difference I was talking about in the linker is that the linker here is called memory.exe. It has a boot size. It uses 256 bytes. It was not RAM, it was flash. 256 bytes of the flash to store the small, let's call bootloader. That is that probe. Is using the flash that is 2 megabytes less the first 256 bytes that are used for the boot, and the RAM is the same. Then here the link file is generated by this build.rs file. This build.rs file that is in the root of the project is generating the linker file everywhere. I don't know why they had to do this. And this is running on the machine that is doing the build, so it can use STD.
What is this code doing? Is it just creating a file?
When you do cargo build, is putting this file basically in all the folder, from what I understood.
Okay.
I am not sure why. That if you go in our cargo config, now you see that here is using the link like we were doing, plus other stuff because it's importing more stuff, so it's linking more. Flip link is another library that is doing handling of the core CPU. And I say that I would show you how to do cargo run and run directly on the hardware. The secret is this line. Instead of cargo run running probe run chip, is running gdb multi-arc. That was the command that we were running before, -q, -x, with a bunch of commands. The bunch of commands are again in a file in the root instead of writing them at every start. And are target, extended, remote, free. That was what I was doing before. Here there are some backtrace limit, asm the mangle. I commented a bunch of stuff that I was not carrying load, so it's writing to the chip. Those commands, instead of starting with a count, is to get out of all the initialization boot sequence, because here we have that Pico probe that is doing magic. So with cargo run, you're running on top of the hardware directly instead of your machine. There is a way to make cargo run on the target only if you want to run on the target with an additional parameter. I think it's written somewhere in the guide that Luciano posted. But in any case, we have Advent of Code exercise 6 for 2021 running on hardware, and I think it's still running. Obviously, being this hardware, if I power it off, it's going off. But if I power it on back again, I don't need to write it again. I don't have to write the software again to the Raspberry PICO because it's already in the flash. So as soon as I power it on, it starts and it executes. And now the GDB is detached. Now GDB is not attached anymore.
Cool.
I could show you, but it's working only one time every 10 tries. If we can debug from VS Code our program. This is not.
Let's give it a shot. We know
Yeah.
there is a little bit of chance there.
It's possible, but it's not that easy. So let me put down a breakpoint. And F5. No, F5 is doing something else. F5. Yeah, started. Terminal. Cargo build. Pim, pum, pam. GDB remote communication. Do we have that running? We still have a GDB connected here. Sorry, we have to have only one GDB running at a time. Not happy if you try to run 20,000. And flash is packet. Okay, let's try another couple of times. And then we give up. Yeah, sometimes it's working, sometimes not. I still have to find out why. Let me try to reset it. Then we run it. No, sorry, but the gods of demo are not in our favor today.
What did we do to make it work last time? Did we just close and reopen Visual Studio Code? Or?
No, we closed and reopen everything. Let me just try to reopen this guy. And function F5. I have to dig a little bit more. And also, doing this, we broke the code inside the chip because it's not programmed anymore, but we know how to do that. See, it's not running now. But if we go with the cargo run, yeah, now it's working. Now, let's try to debug now. I don't believe it will work. No. Okay, nothing. Sorry, it was just a joke.
But you could still show your VS Code files to see like what's the setup.
This is release. My God. See, yes, I can show the setup. Give me a second. I'm doing a mess.
Oh, is it because you were running in release mode?
Could be. Just last try, then I will give up for real. No, okay, let's give up for real.
I swear I saw it working.
Yeah, not today. Like we said, demo gods are not helping us. Basically, in the VS Code folder, you have the ability to put down JSONs that tell what to do, to build, to launch, and to do tasks. This task is the cargo build that is running cargo with build and using a problem matcher for Rust program. Then there is the object copy that is copying the compiled binary in a .bin file. No idea why. It's doing this copy. This is a temporary file. Then here there is a Rust analyzer car. Well, this is the Rust analyzer. It's not useful. This configured is nice, but is okay. Here, configuration. When you receive a request to debug, you build the binary, then you run GDB multi-arc like we did. You connect to localhost 3333. That is what we were doing with our commands. Monitor init, reset, halt, bunch of stuff that are run through the platform, and then it works. What I did last time was commenting those out, Luciano.
Let's try that.
Last time, really this time, eh?
Last time was what, yesterday? Or...
No, sorry, I meant like last try. But this one's really the last try.
There is the last try, the really last try, the super last try, and target down. Is it powered on? Check. Okay, nothing. Demo effect is biting us. In any case, it's possible to debug. It requires a little bit of setup, but basically we are running stuff. Now we broke the flash, but we can program it in a moment. CD Rust RP with the project template. We go with a cargo run. This will be the debug version. We can't. Now also the serial is broken.
It said so. There was an error in the last thing. Error
flashing. Perfect. How everything
so we broke everything.
No, okay, now it's working. Sorry. I had to power it off and on again. I will try to power it off and on again. So, do we want to wrap up here?
I think so. I think
so. This was plenty of stuff.
Yeah, it's a lot of stuff. We will try to put a cleaned up version of all of this in our repository as soon as possible. Yeah. With the link to resources and to I don't know what. And the list of commands to run.
Yeah, list of ways in which you can try to run it in VS Code. Cool. All right. Well, thank you everybody for following along. Or sorry, did you want to say something, Roberto? Before
No, go on. Sorry.
Cool. I wanted to say that you'll be able to find the recording of this entire session on YouTube. The link is in the Twitch channel in the About section. If you're watching this on YouTube, we stream every Monday at 6 p.m. Ireland time on Twitch. So make sure you check out the Twitch link in the YouTube description and follow us so you can be notified when we do new streams. Feel free to leave us comments and PRs. The repo is up on GitHub. It's all public, all open, so any contributions are more than welcome. We should have a banner. Yep, there it is, with the GitHub repo. Everything's well accepted. We're trying to learn Rust, so we're not exactly the best or provide the most idiomatic and most excellent solutions out there. But yeah, like I said, any contributions, any suggestions are super welcome. Thanks everybody. Thanks for the good questions we had today, and thanks Emil, Roberto, for putting all of this together and demoing it.
It was really cool.
Bye.
Thanks. Are we raiding someone, or
we are? You can learn some Zig, which is an interesting alternative to Rust. So see you next time.
See you.